Cool. So me and Xiaowei, we implemented Wordle by leveraging recursive zero-knowledge proofs on Mina. So Wordle, for those of you who don't know, it's a game where a server basically picks a random five-letter word, and your job as a player is to guess that word within 6 tries. So first, brief reminder of what are recursive zero-knowledge proofs. So it's basically a proof that also attests to the validity of a previous proof. So, and a simple real-world analogy would be like if Alice wants to prove that she was in a park 7 consecutive days. So the first day she takes a picture with holding the date, and the second date she takes a picture holding the next date, right, and the previous picture. So, and you can do that recursively for any number of proofs. And what you can also do is you can verify many proofs in a single proof, and that allows for like also for parallelization of producing these proofs, like shown in this aggregation proof on the right side. So why would anybody use recursive zero-knowledge proofs for games? So there are mainly, I wrote down 3 properties that are that recursive ZkApps provide us. So the first one is aggregation. So you have, because in a blockchain world everything has a cost, you don't when the game is running, right, you have all of these steps between players and stuff. So instead of publishing them on chain as transactions, you publish basically the first and the last transaction. And that also ties in with privacy, right? Because you don't wanna, maybe you don't wanna publish everything that happens in the game, and you only publish basically what's a roll-up. And the third one is latency. So because you don't tie in a blockchain during the duration of the game. Now for Wordle, this isn't really important because it's like a slow-paced game, but in the future we could imagine like a truly peer-to-peer shooter or something, like a fast-paced real-time game, and that would surely leverage recursive zero-knowledge proofs because of the latency, because you don't need to broadcast transaction on every state update of the game. Okay, so Wordle, how is it played? So again, the server picks some random five-letter word from a 2,300 word vocabulary. And your job as the player is to guess this word. You have 6 tries. So when you put in a valid word, and then if you hit a letter that is contained in the secret or in the right word, it gets marked yellow if it isn't in the right place. But if it's also in the right place, it gets marked green. And when you guess them all, the game is done. So how do we implement Wordle with Snarky.js? So first we need a way of embedding words. So because the English alphabet has 26 possible letters, we need 5 bits to represent each of them. So that's 25 bits for our words. So that fits nicely. I mean, it's more than enough place in a field element, so we can embed it. Also the clues. So there are 3 possible states that a clue can be in. So either it's yellow, gray, or green, right? So we need 2 bits total. So for each clue, like for our whole word, we need 10 bits. So how does the game process work? So first the server picks some random word from the vocabulary, and it creates a commitment to it. It's important to also salt this commitment with some random large value because we only have 2,300 words in total. So it's pretty easy to create something like a rainbow table and cheat with it. Yeah, and then the server creates like an initial proof, and this proof attests again that the commitment is correct, and it also attests that this word is of valid format, that is from the vocabulary, and so on. And then the player builds upon this proof and makes a guess. So he produces a proof that updates this game state with his latest guess, and this proof also ensures that he didn't change any other state variables in the game. So then the server checks this guess and prepares the clue. So and in case the player got it right, he marks the game as finished. But until then, this is up until 6 steps. This gets like back and forth between the player and the server. So again, right, once the player guesses the word, or once the guesses, the server creates the proof and marks the game finished. So no, the player can't update the proof anymore. And then in the end, of course, you do a roll up and like a normal Mina smart contract and publish it on chain. That's basically it. So yeah, the code is available on GitHub. Here's the link. If anybody is interested, you can take a look at it. It's all public. So yeah, what we did is we implemented the core logic of it, and along with some tests, so to make sure it works properly. But what remains missing is front end, maybe a web front end to actually make regular people be able to play the game. And also, what we didn't implement yet is within the proof, the attestation if the word is actually in a vocabulary. So because we have 2,300 words in total, a way we could implement that is basically build a Merkle tree of this whole vocabulary, and then the server would make a Merkle proof that the word is actually in this vocabulary. And the third thing is some optimizations, because these proofs take a few seconds, I mean like half a minute usually, to actually be processed by a regular computer. We could make some optimizations to make that faster and more snappy. Yeah, okay, that's it. So I'm not sure how much time I have left. Maybe I can show some codes.
Yeah, I think you have like a couple minutes. Is that enough time?
Okay, sure. Okay, so yeah, that's the ZkApp program. So it takes a word, the solution as a private input. It's it also has this salt, and then you hash it, make a commitment, right? And so you initialize it by testing that is correct, and also you initialize all the state variables with like default values. And then you have 2 methods. So update house server, I call it house in this game, but it's the server's method that the server calls. So he takes the player's proof and attests everything is correct there, and he updates the state variables accordingly. So again, if it's the right word, he marks the game as finished, and so on. And here's the player's method. Right, so this one is more simple. So it only updates basically the state with the latest guess, right? Which then the server will check. Here's the roll up. It's very simple. It only checks if the game is finished, basically. And yeah, we also have some tests. So yeah, this is like a whole flow of the game that's being tested, the whole game.